Hi everyone. Just addressing your feedback from today um, on electrochemistry. I was confused by zinc coming out of the metal and copper going back into the metal in the diagram that you illustrated. So I don't know if I'm misinterpreting your comment or if I'm interpreting it correctly. Your question was specifically about zinc going, out of the metal and copper going into the metal. So what I would say to that is zinc isn't coming out. Well, I guess to some extent, zinc is coming out of the metal because the chemical reaction that's occurring here is one where zinc loses two ions. It goes from being in its solid state to going into this ionic state, which can exist quite happily in solution because there are polar water molecules around to surround and solvate the positively charged cation. So that's what you're illustrating here. It's saying that zinc atoms are reacting. They're losing their electrons in this direction, producing zinc ions, and those zinc ions are going into solution. Your comment about copper going into the metal, I would say it's not copper going into the metal. I think it would probably be most accurate to say that copper is going onto the metal. Copper is starting in this 2+ state. Because I have electrons coming into this material, into the solid copper, those electrons can basically be transferred out of the metal onto, so I'm saying here that you have two electrons which are going onto one of the copper ions in this solution. That's really only going to happen if the copper ions are really, really close to the metal surface. When they do that, they become solid copper atoms, and so they plate onto the surroundings of the copper bar, or the copper strip of metal on there. So I hope that clarifies things a little bit. It's not so much copper is going into the metal, but there are electrons that are flowing from this metal electrode and being transferred onto copper ions in solution. Those copper ions, when they become copper atoms are not soluble in solution. So they will tend to come out of solution, and the best place for them to accumulate is on the surface of the copper electrode. The exact opposite is happening over here. Zinc atoms aren't coming out of the metal electrode. They're coming off of the surface, so it's slowly degrading over time as the solid zinc metal is being converted into zinc ions. So hopefully that clarifies your confusion. Do we need to know how to draw out or illustrate an electrochemical cell based on a given cell notation? So I admit I didn't spend too much time on cell notation. I'm not anticipating asking people to draw an electrochemical cell based on cell notation, but as you guys can see, this is a pretty messy way to represent a particular electrochemical cell. They all have the same basic construction. The only thing that might change is the identity of the electrode here, or like the identity of the anode, or the identity of the cathode. That might change, and that's all that's really being expressed in the cell notation. Which chemical species are acting at the anode, which chemical species are acting at the cathode, which species are being oxidized, which species are being reduced. All that information is sort of encapsulated in the cell notation. So I might ask people to interpret cell notation and understand what oxidation reactions are happening, or what reduction reactions are happening. So that's what I would say. I don't know if I would ask people to recreate this drawing on an exam. Well, that would be an interesting question. I think that would be, I think that would not fall into my personal learning outcomes for students. So I don't believe I will be asking that specific question. Certainly not just based on cell notation. But I might ask people to interpret the electrostatic, or the voltage, the standard voltage of a particular electrochemical cell given its cell notation. That's something I might ask. And we can look into that a little bit more in detail on Monday's lecture when we get back to actual electrochemical lecture material. Are oxidation balancing rules going to become an important part in this course? Not really. And I would say, I think I mentioned this in class, my opinion on balancing balancing redox reactions is it's an exercise, and it's not a terribly useful skill, I would say, in of itself. So you'll see, and I'll do a separate video on that. It's a series of algorithmic steps, and it's complicated in the sense that it's different depending on whether you do it in acidic solutions or basic solutions. And I'm of the opinion that you're not really getting any deeper understanding of a redox reaction simply by learning how to balance it. The only thing you really need to know about redox reactions regarding balancing them is that they need to be balanced. They need to be balanced in terms of not only the number of atoms involved, they need to be balanced in terms of the number of electrons being transferred. So they need to be balanced in terms of mass, and they need to be balanced in terms of charge. That they need to do that, I mean, that's something I want people to know and understand. I am not going to be assessing people very much on their ability to balance redox reactions. One thing that you might want to review is assigning redox states, reduction and oxidation numbers, or not reduction and oxidation numbers, just oxidation numbers, oxidation states. I am also going to produce a video on that. And again, I was thinking about how to make best use of the last remaining lecture times we have, and I figured that's something that people had theoretically seen in first semester, so I didn't want to devote much direct lecture time to it in the second semester. But I will have a separate video on that. I would have liked some more examples balancing redox reactions. Yeah, like I said, I will give people some examples of doing that, and I will do that in a separate video. Why is the anode the negative electron when it's losing electrons, and the cathode is the positive electrode when even though it's gaining electrodes? So I think about this in terms of where do electrons want to go, because in the language of electronic devices, anode and cathode, we're thinking about where are electrons going. And electrons, being negatively charged, are attracted to positive charges. Since we're saying electrons are flowing in this direction, it lends itself to the way of thinking that, well, there must be something quasi-positive, quote unquote, about this electrode. There must be some driving force to pull electrons towards the cathode. So we'll say that the cathode is the positively charged electrode because that's where electrons are compelled to go. Conversely, they're moving away from a negatively charged electrode, which is the anode. So that's one way to interpret it. I like to think of the anode as being a source for negative charges. It's where the electrons are originating from. So this is a source of negative charge, and this is a sink for negative charge because we have copper ions here, which will very, very happily grab those electrons and become neutrally charged. So that's the probably the best way to think about it is electrons are coming from here, so this is the source of the electrons, and that's where they're going to. Let's see here. Will balancing redox reactions and assigning oxidation numbers be on the midterm? Absolutely not. They will certainly not be on the midterm. That's this Friday, and on their own, balancing redox reactions, I will hazard and say probably won't be given much time on your final exam. Assigning oxidation numbers will perhaps be, I would say it's an auxiliary skill. It's something that I expect people to be able to do just so you're aware, okay, zinc is in a 2+ oxidation state, copper is in a +2 oxidation state. I mostly just want people to be a little bit more familiar with the terminology. I'm not going to be directly assessing people. It may help you in your reading to review some of those terms, but it's not something that I'm going to be directly assessing people So this was a question I thought was kind of interesting. Could you please post more review questions, specifically those not from the textbook? Could you have some questions that are a little bit more like the ones you're putting on the test? So here's what I would say. I would say the textbook is a good source for questions. And I've tried to change the caliber of my suggested problems. So I have placed a list of suggested problems on the Brightspace website, and I've tried to make those questions slightly more representative of the caliber of questions I would ask on an exam. So I've chosen proportionally, a few more conceptual questions, which are the review questions from the end of chapter exercises in your textbook. So I would say that those are good. I will consider adding on more review questions. I'm of the opinion that the suggested problems out of the textbook and all of your homework assignments are a good selection of problems. And I will consider finding some more if I can, and I will do that. Why is the sulfate ion present in the galvanic cell? Is that always the other species present? Is it present in every galvanic cell? I will say this, there's nothing special about the sulfate ion. I could switch that sulfate ion out for anything. The idea here is that I take a piece of copper metal and I place it into a solution containing copper ions. But I can't just have a solution of only copper ions. If I had a solution that only had copper ions in it, then the entire solution would have this massive net positive charge, and anything else that was remotely charged would be would be drawn towards it. And that's not the case. So the point being that the way we produce for instance, a copper solution is to add in a solid salt of copper sulfate, dissolve that in, and then I will get copper sulfate, so on and so forth. And again, the purpose of the sulfate there is just to serve as a counter ion to the copper ions in that solution. I could switch them out for it could be a copper chloride solution, and so it would be a copper and a bunch of chloride ions. That's a perfectly reasonable or perfectly serviceable solution to substitute in here instead of a copper sulfate solution. Nothing special about the fact that it's sulfate. It's just there to balance out the copper ions that would have already been in that solution before I constructed the galvanic cell. How does adding sulfate to the cathode change copper to copper 2+? So the sulfate ion doesn't do that. The copper ions are not being converted into copper 2+. The addition of the sulfate here is not converting copper metal here into copper 2 ions. That is not happening. The sulfate isn't being added to the cathode. I'd say the best way to describe the sulfate ions in this context is that sulfate is a spectator ion. Just like when you guys were looking at like first semester and you were trying to look at precipitation reactions, you would do that double displacement, and then like two of the ions would crash out as a precipitate, and the other ions would just kind of hang out and do their own thing. They would remain in the solution, in the supernatant. Same basic idea here. The sulfate ion is just there to serve as a balance to the copper ions in the original solution. They are not doing anything to cause this reaction to go this way or the other way. That is being driven by the flow of electrons. It's a redox reaction. Those electrons are coming from the oxidation of the zinc at the other end of the galvanic cell. Does a galvanic cell measure the amount of electrochemical potential? I would say no. The way you measure electrostatic potential is with a device called a potentiometer. So normally what you would do is you would actually, or just a voltmeter, because we'll also call electrostatic potential voltage sometimes. So what you would do is inside of this, or along this, along the wire that's trying to connect your galvanic cell, you would have a voltmeter. And that voltmeter measures the electrochemical potential of the entire electrochemical cell, the galvanic cell. So it's not that the galvanic cell measures electrochemical potential. I would say that the two electrodes in the galvanic cell have a potential difference. You can measure that in this galvanic cell with the addition of a voltmeter. So that's the best way I would describe that. For the quiz on Wednesday, how many questions will be on the quiz? So I've written the quiz, but I'm still, it's not going to be for another 2 days, so I'm reserving the right to tweak it a little bit. But at the moment, it has a grand total of 7 questions. Now, one of those questions is a 3-part question. So already there, I would say it's really like one question with a few parts. And they're not, they sort of follow one from the other. So I would say that that's, maybe a little bit more than one question. And then I have 3 multiple choice questions, and then 1 more additional free response question. So grand total of 7-ish questions. So that might be a little bit longer, so I'm aiming to give people 15 minutes for this one. And if after 15 minutes I look around and it seems like most people still need more time, I'll give a few more minutes, because, again, the main purpose of the quiz is not to be punitive, it's to give people a chance to just think and work under pressure on the problems, and then we'll discuss them afterwards. So hopefully that addresses your concern. As I said, I could very well tweak that in the next 48 hours, so it might end up being a little bit longer, or it could end up being a little bit shorter, depending upon what I do. You didn't teach us oxidation rules. Will we need to know them for the test? I would say, again, oxidation numbers are probably things that you'll need to know. You'll need to be able to recognize, okay, that's copper in its 2+ oxidation state. This is copper in its 0 oxidation state. Even that is probably pushing it. I don't know if I don't imagine I'm going to explicitly ask people, give you a compound, and I will not just ask what is the oxidation state of, like, I'll give you an example. In a substance like nitrogen dioxide, I don't anticipate any questions where I just ask what's the oxidation state of oxygen, what's the oxidation state of nitrogen. We've moved beyond that. I will only be asking people, perhaps making reference to the fact that copper has an oxidation state of 2+. So I certainly won't be directly testing on it. You might want to understand the difference, the idea that chemical species are in different oxidation states. But beyond that, no, I won't be asking any questions about that on the test. And definitely, I would think I can definitely say basically no balancing of redox reactions, because it's not really a useful skill anyway. The only thing that's important is just knowing that they have to be balanced. Will you always have the metals in solution? Will there always be a salt bridge? Are those 2 aspects always necessary? No, not entirely. There are such things as solid-state batteries, where you have an electron transfer between one electrode and another surrounding solid. So you don't have to have solutions as a sink for copper ions. You could have that being converted into some other solid. So you don't need to have solutions, and you also don't need to have a salt bridge. There are ways to construct more complicated, or more, for lack of a better word, clever constructions for galvanic cells. This is just like the most basic. It's sort of the archetypal galvanic cell. So we use this to just sort of differentiate, okay, one part is where oxidation is happening, that's the anode. This part is where reduction is happening, that's the cathode. You connect those 2 with a wire. The flow of electrons causes a buildup of electrons at the cathode, which would prevent the additional flow of electrons. Again, the electrons are being transferred towards the cathode because it's positively charged. If I have a buildup of electrons here, you're essentially slowly negating that positive charge. So what you do is you have a salt bridge, which helps you rebalance that additional negative charge here by having either positive ions come out of the salt bridge, like a potassium positive ion, or having a chloride ion go into the negative cathode where you're losing electrons. And then the chloride here serves to balance out the loss of negative charge at the anode. So that's the only basic thing I want to say about this. This is just giving us our basic construction of how does an electrochemical cell work. These are the key components. Again, you don't always need a salt bridge, and you don't always need these solutions. This happens just to be the most basic and old-fashioned way of doing it. And you will do something somewhat similar in lab next week. It won't look quite like this, but there will be 2 electrodes. You will connect them with an electrical wire, and those 2 electrodes will be connected in some way by a salt bridge, but it won't look quite like this. You'll see next week. It's quite a bit simpler in construction than this, but that's fine. What kind of salt goes into the salt bridge? The most common kinds are really any type of inert electrolyte will serve the purpose of a salt bridge, or yeah, will work in a salt bridge. So it could be potassium chloride, sodium fluoride, ammonium chloride, ammonium nitrate, any electrolyte, something that will spontaneously split. Any salt that will easily split into separate ions and have those ions go into solution, that will work in the salt bridge. Okay, so those are all the comments and questions I got today. If I haven't addressed your questions, bring them to office hours. I'd be happy to answer them. Otherwise, I will see folks on Wednesday. Have a good day.